Hey everyone, so we are looking at section 5.2 today. So in section 5.1, we looked at how to solve system of linear equations in two variables. In this section, we are looking at system of linear equations in three variables, and we will actually use the substitution and the addition method to help us solve these systems. So when we're talking about a linear equation in three variables, if you think of x, y, and z as being our variables, then your equation will have this form: ax plus by plus cz equals d, where your coefficients a, b, c, and d will all be real numbers, and we don't want we don't want a, b, and c to be equal to 0 at the same time, because if they're equal to 0, then we no longer have a linear equation. So that's what we're looking at here when we're talking about linear equation in three variables. Just as an example, this equation can end up looking like x plus y plus 2z equals 9. Now, even though we are calling this a linear equation, and the only reason we call it a linear equation is because it has a form which is similar to our linear equation in two variables like we saw in the previous section, but you are actually not going to get a straight line when you graph this. Now, the solution to a linear equation in three variables is what we call as ordered triple, right? Because there are three variables, x, y, and z, so you should have a answer for x, y, and z, so that's three numbers, so that's why it's called an ordered triple. Just like when we look at an ordered pair, which is just the x and y coordinates, we call it an ordered pair because there are two numbers, so this is an ordered triple because, again, you have three solutions or three numbers as part of your solution that will satisfy the equation. So you can think of ordered triples as the numbers 1, 2, 3, 4, 5, 0, and 3, 4, 1. And all of these are going to be the solution to this example we just looked at, x plus y plus 2z equals 9. And in this case, you can also think of one single equation having infinitely many ordered triples that will become part of the solution set for this linear equation in three variables. Okay, so just like we do with a straight line, these equations also will have infinite number of solutions. Now, when it comes to the graph of these, like I said, they will not be straight lines. What you're actually going to have, because we have three variables, we are going to need to have a three-dimensional coordinate system for each of those variables. We are going to need an axis for each of one. So what we are going to do is, in this three-dimensional coordinate system, we will also have a z-axis which will pass through the origin of your x and y plane. So what you want to think of is your x and y plane as being a flat, you can imagine as a flat piece of paper, your tabletop, or whatever, but it's going to be flat. And your z-axis is actually going to be passing vertically through this piece of paper or through your tabletop, whatever you imagine. So what it does is this third coordinate will actually tell us the distance that is above or below the x and y plane. So it will basically tell you how high up you are from the x and y plane, or how far below you are on the x and y plane. So that's kind of how this z-axis will work out to be. Now, if you look at these figures over here, you will notice we are using the horizontal axis as our x-axis. We have this diagonal axis, which will be our y, and that's going to create our flat surface. And then the vertical axis is our z-axis, which will give you the height above or below your x and y plane. And you can see when we try to graph this equation, x plus y plus 2z equals 9, we can't actually graph that whole equation. So you can see we are actually just showing you the vertices where this plane is going to cross our three axes at. So it crosses the x-axis at the ordered triple 9, 0, 0. It crosses the y-axis at 0, 9, 0, and it crosses the z-axis at 0, 0, 4.5. Okay, so that's where it's going to cross each of the axes, and this point 232 is just a point in the middle of your plane that is formed over here. So when you look at the graph of a linear equation in 3 variables, it's actually going to be a plane and not a straight line. So if you want to think of what a plane would be, just imagine an infinite sheet of paper that basically has no edges. It will just keep going in all directions. So basically it keeps expanding horizontally. It will keep expanding I guess vertically, just depending on how you imagine this plain piece of paper. So just think about an infinite piece of paper will just keep growing in all directions. But you know, obviously it's going to be really difficult to try and draw this infinite piece of paper. So that's why when we are trying to draw a plane, we basically just draw a triangle whose vertices are going to be the points where they intersect the axis at. Okay, so where that plane is going to be intersecting all 3 of these axes. So let's try and see if we can come up with a graph of our own. So we are given x plus 2y plus z equals 6, and they're asking us to graph this in a 3-dimensional coordinate system. So the way your coordinate system works is on the x-axis, the positive side is going to be on the right hand side, which means all the x values will be positive here. On the left hand side, we will have all the negative x values. For the y-axis, the side facing towards us is going to be the positive side, and the side away from us is going to be the negative y values. For the z-axis, you will have the positive z values on the upper half, and you will have the negative z values on the lower half. Okay, so let's go ahead and see. So I've already got my 3-dimensional coordinate system over here. So we are going, like I said, positive on the right hand side, negative on the left hand side for the x-axis. For the y-axis, positive on the side facing towards us, negative on the side away from us. And then for the z-axis, it's going to be positive on the upper part and negative on the lower part, because that's going to be important once we start graphing this, right? Okay, so the first thing we have to do is find the vertices, or otherwise also known as the intercepts. So let's start by finding our intercepts. So let's start by finding the x-intercept. So if you are finding the x-intercept, that means we need to make our y value 0, and we need to make our z value 0. So that means we will end up with x plus 2 times 0 plus 0 equals 6. Of course, these guys will just end up becoming zeros, and we will get x equals 6. So our x-intercept is going to be 6, 0, 0. Remember, these are ordered triples. So that's our x-intercept. Now, let's find the y-intercept. So to find the y-intercept, we'll make the x value 0, and we'll make the z value 0. So this will end up giving us 0 plus 2 times y plus 0 equals 6. Of course, your 0 and 0 will be gone, leaving us behind with 2y equals 6. Divide both sides by 2, and of course we will end up getting y equals 3. So our ordered triple in this case will be 0, 3, 0, and this will be the y-intercept. Okay, so of course the next thing we want to find is our z-intercept. And for the z-intercept, we will make the x value 0 and the y value 0. So that'll end up giving us 0 plus 2 times 0 plus z equals 6. Of course, our 0 and 0 is gone, leaving us behind with z equals 6. So that will be 0, comma 0, comma 6. And this will be our z-intercept. Okay. Now we also want to find one additional point because we just want to make sure that our graph will be in the right location. So just an additional point that we want to find. And to find this point, you can go ahead and say, okay, just select some values for two of the variables and find the third one. Okay, so let's say x equals 1 and z equals 1, and we'll go ahead and find the value for y. So this will give us okay, our original equation. So x equals 1, we are trying to find y, z equals 1, and this equals 6. So 1 plus 1, of course, will give us 2. Move that 2 to the other side, and we end up getting 2y equals 6 minus 2 will be 4. Divide both sides by 2 so that we can get y by itself. And, oops, sorry about that. This will end up giving us y equals 2. So in this case, our ordered triple will be 1 for x, 2 for y, and 1 for z. Okay, and now that we have our ordered triples, we can go ahead and graph these on our three-dimensional coordinate plane over here. So let's start with the x-intercept, which is at 6, 0, 0. So that's going to be this point right over here. Our y-intercept is at 0, 3, 0. So remember, the positive side is here. 0, 3, 0 will be this point. So if it helps, you can go ahead and write your ordered triples down. This guy here will be 0, 3, 0. And then our z-intercept was at 0, 0, 6. So 0, 0, 6 is going to be this guy right over here. And then all you are doing is basically creating a triangle by joining all of these points. So this is kind of what that triangle will end up looking like. And then our additional point, which was 1, 2, 1, is going to be 1 on the x value, 2 on the y value. So 1 and 2 would probably be meeting somewhere over here, and then the depth of or height, I guess in this case, of that 1 from the z-axis will actually end up putting this point, I don't know, maybe somewhere over here. This is always going to be the tricky one to try and graph, just because these, like we said, it's kind of hard to imagine what these three-dimensional planes might end up looking like. So basically this little triangle just shows you where our plane is going to be crossing each of the axes at, but it's really hard for us to draw a whole entire three-dimensional plane. Because, of course, we are trying to draw these on a two-dimensional surface, so it's always going to be a little bit of a tricky thing, but hopefully that gives you kind of a little idea of how the graph of this would work out. So as they're saying here, of course, there is more to a plane than the triangle, but the triangle gives us an idea of at least the location of where the plane is going to be. Now they're saying it is fairly easy to draw a triangle through the intercepts to represent a plane. However, if we try to draw 2 or 3 planes in this manner so that we could see where they are intersecting or how those planes are with respect to each other, it's going to be very, very difficult to do that. And so in this case, we do not use a graphing method to solve these equations in 3 variables. We can refer to the graphs of the equations, but we will not be solving by graphing, okay? So So we're basically going to be using the substitution method, the addition method, or a combination of both of those methods to try and solve these systems. Okay, so let's look at our first type of system here. We are looking at independent systems. So they're saying just like with linear systems in two variables, linear systems with three variables can have one solution, infinitely many solutions, or they can have zero solutions. So they're saying if the three equations that correspond to three planes, if they intersect at a single point, so you can see right here at that single point is where those three planes are intersecting. But again, it's going to be so hard to try and visualize this, but you can kind of see they have those three different colors to show you the three different planes, and they're all only intersecting at that one single point. So we will say there's only one solution to this system, and that solution is going to be a single ordered triple. And systems like these, where you only have one point where all three equations will intersect, or the three planes will intersect, we call them as independent systems. So let's go ahead and look at what the procedure is for trying to solve an independent system in three variables. So we have to basically take this system, which is three equations and three variables, and reduce it down to a system that only has two equations in two variables. So they are saying look for the easiest variable to eliminate. You can use the addition or the substitution method to help us eliminate the chosen variable from two pairs of original equations. So basically you can choose your pairs to be the first or second equation, the second and the third equation, or the first and the third equation. It doesn't matter. Once you have reduced your system down to two equations and two variables, of course, go ahead and solve that system. You will basically get the answers for two of the variables, and then to find the value of the third variable, go back to one of the original equations, substitute the two variables you found out, and then of course you'll find the third one, and we always want to check our final answer in the original system to make sure it works for all three equations. Okay, so let's go ahead and take a look at this example over here. So we're given three equations with three variables, and we want to see how to go about solving them. Okay, so let's take a look at this guy over here. So this will be equation 1, this is equation 2, and this will be equation 3. So they said look for the easiest variable that would be the easiest variable that we can eliminate. And as I am looking at these, I see that my y variable has both positive and negative signs. I've got positive y, negative y, positive y in the three equations. All of our x's are all positive x, but you can also eliminate x by making the other two negative. When I look at the z variable, because my middle equation has a 2z on it, I probably wouldn't bother with the z variable. So in this case, since my y already has a positive and a negative sign, I'm going to go ahead and eliminate y. So the first thing I'm going to do is, since my equation 1 and equation 2 have both positive and negative signs, I'm going to go ahead and add the two equations and eliminate my y variable. So I don't need to multiply them by any other number, because I already have a positive y and a negative y, and they'll cancel each other out. So I'm going to add equation 1 and equation 2. Okay, so that will give us x plus y plus z equals 9, x minus y plus z, 2z equals 1. So when we add these two equations, the positive y and the negative y will cancel each other out. When we add the remaining terms, we get 2x plus 3z equals 10. And let's call this equation 4. Okay, so we've taken our first and second equation and eliminated one of the variables, and you can see this is now an equation with only two variables. Now we want to try and do this one more time. So this time I am actually, because we still need to use equation 3, so how about we add equation 2 and equation 3 this time. So let's add equation 2 and equation 3. So equation 2 is x minus y plus 2z equals 1. Equation 3 is x plus y minus z equals 5. And when we add these guys together, again your negative y and positive y will cancel each other out. Adding the remaining terms gives us 2x plus you are doing 2z minus z, which will of course just give us 1z, and 5 plus 1 is 6. So this guy, we are going to call it as equation 5. So you can see I now have two equations in two variables. So this is what they were asking us to do by taking a system of equation which is three equations in three variables and reducing it down to two equations in two variables. So let's go ahead and write this new system down over here. So I'm going to take 2x plus 3z equals 10, and this was equation 4, and then we've got 2x plus z equals 6, and this was equation 5. So now we need to solve this system just like you did in section 5.1 and find the x and the z values by solving this system. So I'm actually going to use the addition method again here, and you will notice I have 2x and 2x on both my equations. So if I can make one of these two x's a negative, then I can go ahead and add them and my x will eliminate. So what I'm actually going to do is I'm going to take my second equation and I'm just going to multiply it by negative 1. So that'll help us make that 2x into a negative 2x. So multiply each term of the equation by negative 1. First equation will stay the same. So 2x plus 3z equals 10. Now we will have negative 2x, negative z equals negative 6. And when we add these equations together, positive 2x, negative 2x will cancel out, which is what we wanted. 3z minus z will of course give us 2z. 10 minus 6 will give us 4. And of course we can now go ahead and find the value of z. Divide both sides by 2. And we end up getting z equals 2. So once you have found z, now we can go back to either equation 4 or 5 and we can find the x variable. So let's find x, and I think I'm going to use my second equation, 2x plus z equals 6. Z is 2, so we can go ahead and substitute that. Go ahead and subtract that 2, move it to the other side, and we'll end up getting 2x equals 6 minus 2 is 4. Divide both sides by 2, get x by itself, and you will end up getting x equals 2. Alright, so we found our two variables, x and z, which means we're only left to find the y variable. Now, of course, equations 4 and 5 don't have a y in them, right? Because this is where we reduce it down by eliminating y. So to find y, we actually need to go back to one of our original equations. So you can use equation 1, 2, or 3. It doesn't matter which one. I'm actually going to use equation 1 to help us find the variable y. So that's going to be our last step over here. So let's find y by using the first equation, which was x plus y plus z equals 9. So our x value is 2. We are finding y. Z value is 2. and this equals 9. So of course 2 plus 2 will give us 4. Subtract that 4 on both sides, and we end up getting y equals 9 minus 4 will give us 5. And there you go, we have all three of our variables. Now remember, the very last thing we want to do is check all our equations and make sure this ordered triple is going to work. So we have x is 2, y is 5, z is 2. So check in each one of those original variables to make sure this works. So I'm going to start with my first equation, and that's going to be 2 plus 5 plus 2. So 2 plus 5 plus 2 of course gives you 9 equals 9. This is a true statement, so it works for the first equation. Now let's check in the second one, which is x minus y plus 2z equals 1. So that's going to be x is 2, y is 5, plus 2 times z is also 2. So let's see, 2 minus 5 will give us negative 3. 2 times 2 is 4. Negative 3 plus 4 will give us 1 equals 1. So again, a true statement for the second equation. And now we just need to check in the third one, which is x plus y minus z equals 5. So that's x is 2, y is 5, minus z is 2. So as you can see, 2 plus 5 will be 7, 7 minus 2 will be 5, and we end up getting 5 equals 5. So another true statement. So since it's checking out to be true for all of them, we can say that our solution set for this system of equations in three variables is going to be the order triple 2, 5, 2, and that's going to be our answer for this guy. Okay, so this is kind of how the general concept is for solving a system of equations in three variables. You reduce it down from a system which has three equations and three variables, break it down to a system that has only two equations with two variables like we did here, and then find your x and z, the two variables you are left with. And once you find those two, you can go back to any of the original three equations and find the last missing variable. And then of course you check your answer to make sure it works in all three of those equations. Okay, so this was how we work example 2 over here. Alright, now let's look at a system that has infinite number of solutions. So they are saying two planes in three-dimensional space can either be parallel or intersect along a line. So just imagine if you have two pieces of paper with you, they can either be parallel to each other, just like parallel lines, or they can be touching each other. So if they are intersecting each other, because these are planes, right? They are not lines. Since they are planes, or like I said, think of them as being pieces of paper, when they intersect each other, that intersection is actually going to be forming a line. So like I said, two planes in three dimensionals will either be parallel or they intersect along a line. And you can kind of imagine this figure on the left. So you can see we have two planes and they are intersecting at this one single line. So this line right here is where the two planes are intersecting with each other. And since these are infinite sheets of paper, right, this paper keeps growing, so that means we will have a line which is also a line which will keep growing in both directions. So that's why you have infinite number of solutions when two planes intersect in a three-dimensional space. Now they're saying if the planes are parallel, then of course you will have no common point, which means your system will have no solution. And if the two planes intersect along the line, then like I said, we will have infinitely many points, and that gives us infinitely many solutions for that system of equations. So that's what we're looking at here in example 3. So we are given x plus y plus z equals 2 and x minus 2y minus z equals 4. Okay, so let's look at this example over here. So obviously this is two equations in three variables. So our goal should be to reduce it down into two equations with two variables. So when I look at this equation, I can see my z already has one positive and one negative sign. So what we can actually do is just go ahead and add the two equations together, and we can eliminate z in this case. So if we take x plus y plus z equals 2 and x minus 2y minus z equals 4 and add them together, your positive z and negative z will cancel each other out, and we end up getting 2x negative 2y plus y will give us negative y equals 6. Now if I were to rewrite this equation, I can actually start by moving that 2x to the other side. You're left with negative y equals minus 2x plus 6. To get rid of the negative on the y, we can divide everything by negative 1. And that will end up giving us y equals positive 2x minus 6. And we can call this as equation 3. Right? So what happens here is, because these are going to be a system with two equations and two variables, for us to find what our system solution will be, we are actually going to need to take and substitute this either in the first or the second equation. But just before we do that, so basically what we are saying here, when you end up with y equals 2x minus 6, we are saying that our ordered triple x, y, and z is satisfied, is going to be satisfied if and only if both our equations will be y equals 2x minus 6. So it will satisfy both equations, the original ones that we have, if and only if y equals 2x minus 6. Okay, so now as I was saying, we'll need to substitute this in our equation 1 to find what the z value is going to be. So let's go back to equation 1 over here, and that is x plus y plus z equals 2. And what I'm actually going to do is move both my x and my y terms over to the right hand side, and I will end up getting z equals 2 times minus x minus y. And then here I'm actually going to use substitution. So by substitution, I am going to, well, that should be substitute. So I'm going to substitute my equation 3 into my equation 1. So what I'm going to do is basically take this value of y equals 2x minus 6 and substitute that for y in this first equation that we have rewritten. So that would be z equals 2 minus x minus y, but instead of y, I'm going to put in here 2x minus 6. Okay, so let's simplify this. This negative will be distributed, and you will end up getting 2 minus x minus 2x plus 6. Combine all your like terms, so these two guys can be combined together, and these x terms can be combined together, and we will end up getting negative 3x plus 8 when we clean all of this up. And let's call this equation 4. Alright, so we have y equals 2x minus 6. We have z equals minus 3x plus 8. So what this is basically telling us, and we know this is a system of equations that will have infinite number of solutions, we have both our y and z in terms of x. So the idea is if you know what value of x we can use, then just by plugging those values of x into both of these equations, we can come up with our solution for this system over here. So let's say if you wanted to use, I don't know, x equals 1. So we would have x equals 1. For y value, we would do 2 times 1 minus 6, which would be 2 minus 6, which would give you negative 4. So y would be negative 4. For z, it would be negative 3 times 1 plus 8, which would be negative 3 plus 8, which of course gives you a 5. So in the same way, you can find infinite number of ordered triples which would satisfy this equation. So this is not going to look like what you saw in the previous example. We're not going to get a solution set like that, because that one was only where your three planes were meeting at one single point. But here, of course, they are meeting at a single line, right? One line. So you're going to have infinite number of solutions. So when you write your solution set down, it's actually going to be pretty interesting how you write it down. So we would use the set builder notation again, like we had seen in the previous section. So this would be the ordered triple x, y, z. And then here we would say y equals 2x minus 6 and z equals minus 3x plus 8. So this is one way of writing our solution set, and this would be in terms of x, right? Because y is defined in terms of x and z is also defined in terms of x. Now, you can also rewrite these in terms of y and z also. So let's say instead of writing these as y equals 2x minus 6 and z equals negative 3x plus 8, what if we wanted to write this as in terms of y, let's say? So we will need to rewrite these equations. You would start by taking y equals 2x minus 6 and getting x by itself. So we would go ahead and move the 6 to the other side. Then divide by 2 to get the x by itself. And of course, that would end up giving us, this should be separate, there we go. You will have 1/2 y plus 3 equals x. And then we would need to get the z also and rewrite it in terms of y. So what we would do is replace that x with the 1/2 y plus 3 from here and simplify this. So this will end up giving us, remember, you need to distribute this 3 inside the parentheses. So this will give us negative 3/2 y minus 9 plus 8, which will of course end up becoming negative 3/2 y minus 1, and this would be in terms of z. So when you write your solution set for this, these equations, they would end up looking like x, y, and z as our ordered triple, and then we would say x equals 1/2 y plus 3 and z equals, oh, what did I do? Okay, I just saw what I did. This should be negative 3/2 y. Negative 3/2 y minus 1. So this is how you would write it if they wanted your answers to be in terms of y, which means x and z have to be defined in terms of y. Okay, and in that same way, if they wanted us to define this in terms of z, then we would need to rewrite this as, we would start with z equals negative 3x plus 8, but now we want to get x by itself, so start by subtracting 8 first. Then you would have z minus 8 equals negative 3x. Divide everything by negative 3, and that would end up giving us negative 1/3 z plus 8 over 3. And of course now this would equal x. We would need to get y in terms of z also. So you would do 2 times this whole mess, negative 1/3 z plus 8 over 3 minus 6. So again we would distribute this guy inside the parentheses and we would have negative 2/3 z plus 2 times 8 would be 16 over 3 minus 6. And of course you would need to go ahead and combine these two, simplify that, and we should end up getting y equals negative 2/3 z minus 2/3. I'll let you guys go ahead and simplify that. 16 over 3 minus 6. Okay. Alright, so once we have this, then we can write our solution set. Which would now be x, y, and z. And you would say x equals negative 1/3 z plus 8 over 3. And y equals negative 2/3 z minus 2/3. So this is of course if they want us to write our solution set in terms of z. So when you are working through your homework, you will need to see how they want you to write your answers. Is it going to be in terms of x? Is it going to be in terms of y? Or is it going to be in terms of z? So since this was a system that had infinitely many solutions, you can see just a little bit of a twist on how we actually solve these types of examples. Okay, so that was our number 3. Now we are saying a line in 3-dimensional space does not have a simple equation like a line in a 2-dimensional coordinate system, right? Because you of course have 3 variables instead of 2 variables. So in this example that we just got done looking at, we had our x variable, and then y was defined as 2x minus 6. Z was defined as minus 3x plus 8, right? And they're talking about how we got y equals 2x minus 6 and z as negative 3x plus 8. So if you're defining your ordered triple in terms of x values, this will be basically a point on the line of intersection of the two planes for any value of x, right? Any real number x. So we are saying the ordered pairs 0, 6, 8, 1, negative 4, 5, and 2, negative 2, 2 will all be points that will satisfy both the equations in this system. And of course, they are going to be part of that line, which is where the two planes are intersecting. So that's what they are just saying, that a line, the equation of a line is not going to be similar to what you had seen in a 2-dimensional coordinate system. Okay. Now the next example we want to look at is for something like this over here, where you have 3 planes that are intersecting at one single line. So what happens when 3 planes intersect at one line? So what that solution would look like. So that's example number 4. So let's go ahead and take a look at that. So okay, so again, this will be our equation 1, equation 2, and this will be equation 3. So again, we are given 3 equations with 3 variables. So we want to try and reduce this down to 2 equations with 2 variables. So figure out which variable you think is going to be the easier one to eliminate, and eliminate that. So in this one, I am seeing that I have plus z minus z plus z. So I'm going to eliminate z. Of course, y also could be eliminated since they also have the plus and the minus. But let's go ahead and eliminate z in this example. So to eliminate z, I'm going to go ahead and add equation 1 and equation 2. So let's see, that will give us x plus y plus z equals 1, x minus y minus z equals 3. So when this happens, you will notice that my x will of course stay, positive y, negative y cancels out, and positive z and negative z cancels out. So that will end up leaving us with 2x equals 4. Divide both sides by 2, and we end up getting x equals 2. So this will be equation 4. Now we can also go ahead and, since we need to use equation 3 also, how about we go ahead and add equation 2 and equation 3 and see what happens. So that's x minus y minus z equals 3. 3x plus y plus z equals 5. So again, we're adding both of these equations. So negative y, positive y cancel out. X's will of course stay. Negative z, positive z cancels out, and that adds up to give us 4x equals 8. Divide both sides by 4, and you end up getting x equals 2. And of course, you should notice that we got the same result as equation 4, right? So equation 5 came out to be the same thing as equation 6. So that basically tells us that both of these equations are dependent, and that means our original system is going to have infinitely many solutions. So anytime you end up getting the same result, that tells us that our system has infinitely many solutions. So let's see how we need to write this solution set down. Okay, so what we're actually going to do is we're going to start by replacing x equals 2 in our original equations, and let's see what we end up getting. So we have x plus y plus z equals 1. So that's going to be x is 2 plus y plus z equals 1. So if I go ahead and subtract 2, we will end up getting y plus z equals, oh, that'll be negative 1. Okay, so if I try to solve this for y by moving z to the other side, I will end up getting y equals negative z minus 1. Or if I try to get z by itself and move y to the other side, I will end up getting negative y minus 1. So this is the form I get from the first equation when we plug in for x equals 2. Now what if we try the same thing on our second equation? So our second equation was x minus y minus z equals 3. So again, x will be 2 minus y minus z equals 3. Again, we'll start by subtracting that 2, move it to the other side, and we've got negative y minus z equals 1. Divide everything by negative 1, and that will end up giving us y plus z equals negative 1, which is similar to what you got from equation 1. So if we rewrite this, we will get y equals negative z minus 1, or get z by itself. That would be negative y minus 1. And again, this is happening because these equations have infinitely many solutions. I'm going to try this for my third equation also, which was 3x plus y plus z equals 5. So that's going to be 3x, x is 2, plus y plus z equals 5. 3 times 2 is 6. So let's go ahead and subtract that 6 on both sides, and we end up getting y plus z equals negative 1, again similar to the other two equations. So get y by itself, we have negative z minus 1, or get z by itself, and we have negative y minus 1. Okay, so when we actually write our solution set down, it will depend if they want us to write this in terms of x or y. So if they want this in terms of y, then our order triple is going to be x is 2, of course we got that, but then for in terms of y, you would write y over here, and then you would have z equals negative y minus 1, and this is when they want us to write this in terms of y. So you will say y is any real number. Okay, so this is going to be one way of writing your solution set here. Now if they want this in terms of z, of course we still have x equals 2, but if they want it in terms of z, then you are going to say y equals negative z minus 1, and then for z you're just going to write z, and we will say z can be any real number. So we basically got one constant answer for x. We got x equals 2. So x will always be 2 when you write your ordered triples. But then depending on, do they want us to write this in terms of z or in terms of y, you're going to have to rewrite z either in terms of y or y in terms of z. So again, just because these guys have infinite number of solutions, your ordered triples and the way you write your solution sets are going to look a little bit different than just having 3 numbers in there. Okay, so this would be our solution to problem number 4. All right, let's see what they're saying here. So basically they're saying if all equations are equivalent, if all the equations are the same, then the solution set to the system is going to be the set of all points that satisfy any one of the equations. So if all 3 equations are equivalent, which, think about this, if I take my second equation and divide it by 2, I'm going to get the same answer as equation number 1. If I take my third equation and divide the whole equation by 3, then the answer I get again is going to be similar to that equation number 1. So equation 2 is just the first equation multiplied by 2. Equation 3 is again the first equation multiplied by 3. So that's why they are all equivalent. So whatever is the solution to one equation is going to be the solution set for your entire system. So that's kind of what they're talking about here. Okay, so we have seen independent systems where the 3 planes intersected at one point. We have seen solutions for systems that have infinitely many solutions, which is what we did in the previous 2 examples. Now let's look at an example for an inconsistent system. So here they're saying there are several ways that 3 planes can be positioned so that there is no point on all 3 of the planes. So they're basically saying that these 3 planes will not be intersecting at one single point. So they're saying for the following figure corresponds to a system where there are 3 ordered triples that satisfy 2 equations, but there's no ordered triple that satisfies all 3 of the equations. So you can see 2 of these planes are intersecting at a straight line, right? So these 2 planes are intersecting at a straight line. These 2 planes are intersecting here at a straight line, and of course these 2 planes are intersecting at a straight line. But between all 3 of them, there is not even a single common point. So when you have planes that may have this kind of a setup, this kind of a configuration, and if there are no points that are common to all 3, we would say that the system is inconsistent and it has no solution. And they are saying it is easy to identify a system with no solution because you will end up getting a false statement when you try to solve it. Okay, so let's go ahead and take a look at what happens when we try to solve this example 5 over here. Okay, so again, this is a system with 3 equations and 3 variables. So we want to pick an easy variable to eliminate. So you can again eliminate y or z, but let's go ahead and see what happens when we try to eliminate the z variable. So again, this will be my equation 1, this is equation 2, and this guy will be equation 3. So how about we go ahead and add equations 1 and 2. Okay, so that will be x plus y plus z equals 1, x minus y minus z equals 3. And when we add these together, it looks like x will stay, positive y cancel out, positive z, negative z cancel out, leaving us behind with 2x equals 4. So let's solve for x, divide both sides by 2, and you get x equals 2. Let's call this equation 4, okay? Alright, so since we used equations 1 and 2, now let's go ahead and eliminate the z variable by adding equations 2 and 3. Oops. Okay, there we go. So this will give us x minus y minus z equals 3, and then this guy will be 3x plus y plus z equals 7. So we're adding the two equations, and again our x terms will stay, negative y, positive y cancel out, negative z, positive z cancel out, leaving us behind with 4x equals, what will that be, 10. Get x by itself, divide both sides by 4, and 10 over 4 can be reduced down, which will basically become 5 over 2 because 2 will be common between both of them. And you can see we did not get the same x value over here, and this is happening because our two equations are not equal, which means that our system is inconsistent, so there is no solution. So this is an inconsistent system, and we have no solution. But just to show you what happens, let's say if you were to plug in this value of x equals 2 into our three equations, equations 1, 2, and 3, let's see what happens in this case. So in equation 1, x plus y plus z equals 1, we will have 2 plus y plus z equals 1, subtract that 2, we end up getting y plus z equals negative 1. Okay, now let's see what happens when we substitute this in our second equation. So that's x minus y minus z equals 3, so that's 2 minus y minus z equals 3, subtract that 2, and we end up getting negative y minus z equals 1. To get rid of the negative on our variables, let's divide everything by negative 1, and we end up getting y plus z equals negative 1. So far, both of these are the same, okay? Now let's see what happens with the third one. 3x plus y plus z equals 7. So that would be 3 times 2 plus y plus z equals 7. So that's 6. Subtract that from the 7. And we are getting y plus z equals 1. And you will notice this guy came out to be different from these two solutions that we got from the first two equations. So again, you can see that in this case, if we did a substitution between these two equations. So if you did this as y plus z equals -1 and y plus z equals 1, since we have the same term y plus z and y plus z on the same side, this basically ends up giving you -1 equals 1, which is a false statement, because -1 of course is not equal to +1. So when you get a false statement, this again should tell you that, hey, we have an inconsistent system, and of course that means we have no solution to this system over here. So even if you thought, okay, I got two different answers for x over here, and you still don't catch it, when you try to put this into your three original equations, you will see we will end up getting a false statement, because one of these equations, like you saw in this case, is not matching because I got a +1 instead of a -1. So this is where we're running into our false statement, and this is what tells us, hey, we have no solution to the system here. Okay, so this is kind of how our three different types of solutions will end up looking like, based on, do you have one solution, infinitely many solutions, or no solution. Okay. All right, now let's take a look at this next example here. So they are saying, just as we find the equation of a line from two given points, basically remember you have to find the slope, and then you can find the equation of the line by using the point slope form. They are saying we can also find the equation of a parabola, which would be in the form y equals ax squared plus bx plus c, if we are given three different points. So to find the equation of a parabola, basically we would need 3 points to help us determine the three variables a, b, and c, which is the coefficient a, b, and c here in the equation of our parabola. And they are saying as long as these 3 points are not collinear. When we say collinear, we're basically saying they should not be in one straight line with each other, right? They should be kind of spread out on the coordinate plane, and they should not be in the same straight line. We can find the system of three equations in three unknowns, three variables, and we will basically end up with a unique solution. So let's see, if we are given 3 points, how can we find the equation of a parabola? Now, of course, when we're talking about a parabola, we are talking about a two-dimensional coordinate system, right? So you will have ordered pairs and not ordered triples. So here are our 3 ordered pairs, and based on that, we need to try and come up with our 3 different equations with 3 variables, and then solving that will help us come up with the equation of our parabola. So let's go ahead and take a look at this example here. Okay, so what we're going to do is, of course, remember these are your x and y values, right? Because these are ordered pairs. So what we are going to do is we are going to take this equation of the parabola, y equals ax squared plus bx plus c, and for each of the 3 ordered pairs, we are going to put it in this form of the parabola and try to come up with our 3 equations for our system of equations. So let's start with the first ordered pair, -1 and 1. So we're going to take y is 1. We don't know what a is. X is -1 plus b times x. Again, x is -1 plus c. When you simplify this, you will end up with 1 equals -1 squared will become +1. So that's going to leave this guy as +a. B times -1 will become -b plus c. So this will be the first equation for our system. Now let's do one with the second ordered pair. So that's 1 and 3. So again, y value equals 3. A x equals 1, so that's 1 squared plus b times x is 1 plus c. So of course this will end up giving us 3 equals a plus b plus c, right? So this guy here will be our second equation, so equation 2. And then using the third ordered pair, which is 2 and 7, we will be able to come up with our third equation. So now y value is 7. Oops. A times 2 squared plus b times 2 plus c will end up giving us, of course, 2 squared will be 4, so this becomes 4a plus 2 times b will be 2b plus c, and of course this gives us our equation 3. Okay, so let's go ahead and write all three of these down. Now I prefer having my 1 on the other side and my a, b, c on the left hand side, so this will be a minus b plus c equals 1, a plus b plus c equals 3, 4a plus 2b plus c equals 7. So again, this is equation 1, equation 2, and this guy will be equation 3. Now once you come up with your system, you have to try and see which variable you can eliminate. So you can eliminate pretty much any one of them, but since I already have a negative b and a positive b, I'm going to go ahead and eliminate the b variable, but of course you could have worked with a, b, or c, whichever one you prefer. So let's do b over here. So we are going to eliminate b. And the first thing we are going to do is add equations 1 and 2. So let's see, that will give us a minus b plus c equals 1, a plus b plus c equals 3. And when we add these guys, of course, your negative b and positive b will cancel out, leaving us behind with 2a plus 2c equals 4. And this will be equation 4 for us. Then we need to see what we can do with equation 3 over here. So how about we add, since my equation 1 is the one that has the negative sign on it, and I need to, of course, use equation 3 also, because I've already used 1 and 2, which means I have to use equation 3 in this next one. So you can see how I have a positive 2b in equation 3, so that means I need to multiply my first equation by the number 2 so that I can have negative 2b that will cancel out the positive 2b. So I'm going to take 2 times equation 1, and then I'm going to add that with equation 3. So when you do 2 times equation 1, and let's do that over here, so 2 times equation 1 will end up giving us 2a minus 2b plus 2c equals 2, right? Okay, so that's going to be for equation 1 multiplied by 2, 2a minus 2b plus 2c equals 2, and then equation 3 will stay as it is, which is 4a plus 2b plus c equals 7, and then when we add these two equations together, that negative 2b will cancel out with the positive 2b, which is exactly what we wanted, and then we'll end up getting 6a plus 3c equals 9. Now, you can leave it the way it is, but when I look at this equation, I actually see that all of them have a 3 in common. So if I divide each one of these terms by 3, I can actually simplify this equation, and 6 goes into 3 2 times, so you'll end up with 2a plus 3 divided by 3 will just leave us behind with a c, and then 9 divided by 3 will of course give us 3. So you can simplify this equation, and our equation 5 will now be 2a plus c equals 3. And like I said, if you don't simplify it, it's okay. It will clean up when you move forward. Alright, so let's go ahead and write our system down. So we have reduced it from 3 equations in 3 variables to 2 equations in 2 variables. So we have 2a plus 2c equals 4, 2a plus c equals 3. So this guy is equation 4. This one is equation 5. Now you can use substitution or you can use the addition method to simplify this system down. So what I am actually going to do is I am going to add equation 4 with -1 times equation 5. So what I'm actually trying to do is make this 2a on equation 5 a negative 2a, so that I can go ahead and cancel out my a terms and basically come up with the value for c. Okay, so we are going to take equation 5 and multiply it by -1. So this will end up giving us negative 2a negative c equals -3. Okay, so let's go ahead and combine these. So we've got 2a plus 2c equals 4. Equation 4 stays as it is. And then equation 5 has now become -2a minus c equals -3. So when we add these two equations together, positive 2a, negative 2a cancel each other out. 2c minus c will of course end up giving us c equals, and then 4 minus 3 gives you 1. So you can see we came up with the value for c. And now that we have the value for c, we can go back and find the value for a. And to find a, you can use any one of these two equations, either equation 4 or equation 5. I'm just going to use my equation 5. 2a plus c equals 3. If c is 1, then we subtract that 1 on both sides, and we end up getting 2a equals 2. Divide both sides by 2 to get a by itself, and you will of course see that a comes out to be 1. So we found the value for c, we found the value for a, which means now we need to go back and find the value for b, which was our third missing variable here. Now to find b, of course equations 4 and 5 will not work because this is where we had eliminated b. So you need to go back to one of the original equations that we had, which is going to be one of these equations 1, 2, and 3. We've got, I think I'm going to use equation 2. A plus b plus c equals 3. So a plus b plus c equals 3. We know a is 1, c is 1. So of course 1 plus 1 will add up to 2. When we subtract 2 on both sides to get b by itself, this is interesting. Looks like b also came out to be a value of 1. So you've got a equals 1, b equals 1, and c equals 1. So when we put this together, the equation of the parabola the general form is y equals ax squared plus bx plus c. So now that we know our a, b, and c values, we can go ahead and plug it in. So that's 1 for the a, 1 for the b, and 1 for the c. So just cleaning this up, you basically end up getting x squared plus x plus 1 as the equation of the parabola. And this parabola, y equals x squared plus x plus 1, is going to be passing through all three of these points. So that's kind of how you can kind of think of this actually as an application of where do these three equations with three variables comes into play. So as an application, this can actually help you come up with the equation of the parabola if you know the 3 points that your parabola is going to be passing through. And again, remember, those 3 points cannot be in the same line, straight line with each other. So this is how your solution would come out to be, and this is of course an example of your independent system, because basically all 3 of these planes are meeting at one single point. Okay, alright guys, so this was the example 6 over here, and then we had one more example. I believe this is the last one here, and this is another application where they're talking about 2 adults, 1 student, and 1 child paid a total of $14 for admission to the zoo. 1 adult, 2 students, and 1 child paid a total of $12, and then 2 adults, 2 students, and 3 children paid a total of $19. So they want to know what the admission prices to the zoo are for adults, students, and children. So if you look at this, again, we can use A for the adult ticket prices or admission prices. We can think of S for the students, and of course C for the children's ticket prices. So they're telling us 2 adults, 1 student, and 1 child paid $14. So that's 2 adults, 1 student, 1 child paid $14. So that's how you come up with your first equation. They're telling us 1 adult, 2 students, and 1 child paid $12. So that's 1 adult, 2 students, and 1 child. They paid 12. And then 2 adults, 2 students, 3 children paid a total of 19. So 2 adults, 2 students, and 3 children paid a total of $19. So once you have your 3 equations in 3 variables, again, we can go ahead and solve this. So let's go to look at this example here. Okay, so I've already got our equations written down. So of course you can see all of your variables have a positive sign in front of them, so that means we need to figure out which variable to eliminate. And you know, in this case, I think I'm actually going to go ahead and eliminate variable A. So again, let's call this guy as our equation 1, this one as our equation 2, and the last one, of course, will be equation 3. So let's go ahead and add equations 1 but in this case, I'm going to add equations 1 and 2, but I need to make one of these into a negative 2a and one of these into a positive 2a. So since equation 1 already has a positive 2a, let's make equation 2 have the negative 2a, which means we need to take our equation 2 and multiply it by negative 2 in this case. So when we do that, when we multiply our second equation with negative 2, we will end up getting negative 2a, negative 4s, negative 2c equals negative 24. So first equation will stay the same, 2a plus s plus c equals 14. Equation 2, after we multiply it with negative 2, of course we have negative 2a, negative 4s, negative 2c equals negative 24. So when we add these guys together, your positive 2a, negative 2a cancels out. And then when we add the remaining terms, we will end up with negative 3s. Let's see, negative c equals negative 10. Okay, so let's see what will we end up getting. Let's call this guy equation 4. Now, since we used equations 1 and 2, let's go ahead and add equations, maybe 1 and 3. So same thing, we'll add equation 1 And of course you can see I have positive 2a and positive 2a for both equations 1 and 3. So I'm actually going to multiply equation 3 by negative 1. Okay, so we're going to take this guy and multiply it by negative 1. So that will end up giving us negative 2a, negative 2s, negative 3c equals negative 19. Equation 1 again will stay the same. So 2a plus s plus c equals 14. And then we've got negative 2a, negative 2s, negative 3c equals negative 19. Let's add these guys together. Positive 2a, negative 2a will again cancel each other out. Combining the other terms will give us negative s, negative 2c equals negative 5. And of course this will make equation 5. Okay, so let's go ahead and write that system down. We've got negative 3s, negative c equals negative 10, negative x, negative 2c equals negative 5. So at this point, let's see if we can eliminate, it really wouldn't matter, you can eliminate s or c, but let's go ahead and try and eliminate c, I guess, in this case. So this is equation 4, this guy is equation 5. We are trying to eliminate c. So for that, since I have negative 2c for equation 5, let's make that positive 2c for equation 4. So how about we multiply our equation 4 by negative 2. So multiplying equation 4 by negative 2, and we'll keep equation 5 as it is. So multiplying this guy by negative 2 will end up giving us, let's see, positive 6s, positive 2c, and that will be positive 20. So positive 6s, positive 2c equals positive 20. Equation 5 will stay the same, so that's negative s minus 2c, and that's equal to minus 5. When we add these two equations together, okay, so when we add these two equations together, of course your positive 2c and negative 2c will cancel out, and we end up getting 5s equals, what's that, 15. Divide both sides by 5 to get our s by itself, and we get s equals, of course, 15 divided by 5 will give us 3. So we got our value for s, and of course this represents our ticket prices for the student tickets. So these are students' prices. Okay, now since we have found the s, we can go back and find c. So to find c, you can use again any one of the equation 4 or 5. So how about we use equation, you know what, let's use equation 5 over here. So that's negative s minus 2c equals minus 5. And you know, we could have actually gotten rid of those negatives. I didn't really think about that, but it's okay. So s is 3, and we're trying to get the value for c, children's tickets. So let's start by adding that 3 over there, and that leaves us behind with negative 2c equals, looks like negative 2. Divide both sides by negative 2, and we end up getting c equals 1, right? And this will of course mean the children's tickets are only going to be $1 each. that's $1. For children's tickets. Okay, so we have found the student ticket prices and we have found the children's ticket prices. So of course now we need to do is find what the adult ticket prices are going to be. So for that we need to use one of these original three equations. And how about we use equation 1 over here, 2a plus s plus c equals 14. So we are finding a. So 2a plus s plus c equals 14. Student tickets are $3, children is 1. So of course that will add up to 4. Subtract 4 from both sides. We end up getting 2a equals 10. Divide both sides by 2. Get a by itself. Oh. And we will end up getting a equals 5, which again tells us that adults are paying $5 to get into the zoo. Okay, so $5 for adults, $3 for students, and $1 for children. There you go. So this is how your application for a system in 3 equations with 3 variables would end up looking like. Okay, so I hope these examples have given you an idea of how to solve a system which has, like I said, 3 equations with 3 unknowns. So look through these handouts again, the video, and let me know if you have any questions. So I will see you in class next time. Be careful, be safe everyone, enjoy, and I will see you in class. Bye-bye.